Across 12 years of trials and training, you proved yourself a worthy candidate who could survive anything. But the terrifying truth was this: not a single human has ever experienced before what you're about to face. What months of isolation in an infinite dark void would actually do to your mind. How your body would begin to fall completely apart under cosmic radiation, microgravity, and a dozen other forces long before you even reach your destination. What it actually takes to reach Mars. Publicly, Aurora 1 was presented as a joint NASA-SpaceX demonstration, a PR-crafted narrative to keep the public comfortable. But the classified version behind was something entirely different. Aurora 1 was not a rehearsal. It was a full 9-month transit to the Red Planet, with 1 astronaut on board, and no confirmed plan to bring that astronaut home. The reasoning behind that mission was simple. The loss of a full crew would collapse Mars exploration for centuries. But an unofficial mission like this could pave the way for future manned flights to succeed, without the political fallout of losing 6 people in front of the entire world. Human experimentation rules forbid exposing astronauts to non-rescuable missions. Classified programs, however, operate under different standards. Your mission existed to determine how much damage 9 months in deep space can inflict, and whether the human mind can endure isolation no one has ever experienced. They needed real, non-simulated data. That was the purpose. For 12 years you trained to be the pilot, the mechanic, the engineer, the medic, the EVA specialist, and the mission commander, because you would need to be all of them. You learned to diagnose your own symptoms, repair every system in a habitat, manage life support, and operate robotic arms for surface assembly. You spent more than a year inside an isolation chamber. Your data would determine whether future crews ever leave Earth. Your survival timeline would directly influence the next century of space exploration. They wanted you to feel honored, and maybe, in a way, you did. You were going to Mars without a return ticket, and no training could truly prepare you for what you were about to experience. The cost of Aurora 1 was estimated around $8 billion, a number so high that the mission had to be reduced to its absolute essentials. Only one launch system could support it, SpaceX's Starship. Nothing else on Earth could lift the mass required for a human Mars mission. Returning a Starship home would also demand hundreds of tons of additional propellant, so Aurora 1 wasn't designed to return. The spacecraft that carried you to Mars would stay there, and so would you. 2 other starships had to be sent ahead of you for equipment pre-deployment. A human can't land on Mars without infrastructure already waiting on the surface. Kilopower nuclear reactors, life support, communications. Those cargo flights delivered the backbone of the mission. A kilopower nuclear reactor was a slim metallic tower, barely taller than a person. Installed 20 to 30 meters from your habitat, it would provide a steady 10 to 40 kilowatts of power, the only reliable electricity source on a planet where sunlight is weak and dust storms can last months. A MOXIE-derived on-site utilization unit was also pre-deployed. Its purpose was simple but critical: prove whether the Martian atmosphere could be converted into breathable oxygen and possibly future rocket oxidizer. Not for your mission, for the crews who might come after you. The cargo landers also delivered inflatable habitat and 2 unpressurized rovers, along with robotic manipulators designed to help you construct surface infrastructure without another human on site. Solar arrays were included as redundancy, enough to support operations if kilopower units failed. Even an ascent stage test craft was sent beforehand. It wasn't fueled. It existed purely to study how ascent engines behave after months in Martian conditions. data required for future crews. Only after all of that equipment was confirmed on the Mars surface did your own starship prepare for launch. The vehicle carrying you included a radiation storm shelter, life support system spares, food and water for the journey, a medical kit, EVA suits and replacements, a portable lab bench, a 3D printer with feedstock, and everything else required for a 9-month trip across deep space. Launch day begins the same way every astronaut describes it, with checks, cold air, and you strapped into your seat. While the cabin seals and the spacecraft runs its last diagnostics, mission control voices filter through your headset. Go for fuel. Go for flight. Go for launch. At T0, the engines ignite. The force is immediate, a rising push of 1.5 G that compresses you into the seat as the vehicle lifts from the pad. The vibration is violent. It is the roar of metal straining to break free of Earth. Within the first minute, you reach the point of maximum aerodynamic pressure. The starship throttles down slightly as the hull fights the thickest part of the atmosphere. Outside, velocity climbs toward 1,000 meters per second. Inside, the G-load stays manageable, around 3 times your weight, uncomfortable but familiar. Your vision blurs slightly at the edges, your breathing becomes deliberate. A few minutes later, the first stage cuts off. The booster drops away, and the upper stage ignites almost instantly. The acceleration increases, smoother but stronger, pushing you toward orbital velocity. 8.5 minutes after liftoff, the burn ends. The engines fall silent. Microgravity begins, a sudden absence of weight that feels like your body is falling in every direction. The spacecraft coasts into low Earth orbit at nearly 7.8 kilometers per second. Earth curves beneath you, bright and impossibly close. For the next hour, everything is about system checks and orientation maneuvers. Then comes the burn that sends you away from Earth forever. When the Trans-Mars injection begins, the engines light again, but this time the acceleration is gentle, only a fraction of a G. For 6 to 12 minutes, the spacecraft increases its velocity just enough to stop orbiting Earth and start orbiting the Sun instead. When the burn ends, you are no longer in Earth's gravity well. You are a separate object following your own solar trajectory, one that will intersect Mars months from now. This is the point of no return. The spacecraft is moving too fast and carries too little propellant to cancel its velocity. Even if you turned the ship around and fired the engines continuously, you would not be able to fall back to Earth again. You are committed because the universe has locked you onto a path. Earth begins to shrink behind you, first a sphere, then a pale bead of light suspended in darkness. A few hours after liftoff, the realization settles in. You are now farther from rescue than any human in history. The first few hours after the Trans-Mars injection burn feel deceptively calm. The engines have shut down, and the ship has settled into its cruise configuration. You're now riding a Hohmann transfer orbit, a precise, efficient trajectory that turns the spacecraft into a free-fall projectile moving through the solar system. Fluid shifts upward into your skull, creating a dull pressure behind your eyes. You feel slightly nauseous, slightly disoriented from the very first moments. The spacecraft performs small course corrections during the first day, and outside the hull, for the first time in your existence, there is no Earth magnetic field protecting you from radiation. Galactic cosmic rays begin bombarding your body with the unstoppable particles, like bullets. When one passes through a cell, it tears chemical bonds apart, slicing DNA in ways your repair systems can't fix. You don't feel anything special. By the end of the first week, microgravity begins dismantling you in predictable ways. Your muscles weaken, and so is your cardiovascular system, because it no longer has to fight gravity. You exercise daily because you have to, but even with perfect discipline, the atrophy happens anyway. Somewhere around day 10, you start to feel the psychological weight of complete solitude. The sounds of fans, pumps, and CO2 scrubbers become the only soundtrack of your existence. The communication delay with Earth stretches into minutes. Cosmic radiation continues accumulating, and every day you begin to feel more and more fatigue. Your head aches more often, and thinking feels a little slower, just occasionally. By day 40, the spacecraft is deep into the void. The windows show only an infinite blackness, and your mind is starting to lose its frame of reference. You begin to experience a known psychological phenomenon, the deep space effect. It's the combination of sensory deprivation, perpetual silence, and the awareness that you are absolutely alone in space. You move through routines automatically, eat because you're supposed to, sleep in short intervals. You begin forgetting small things, where you put a tool, what step comes next in a checklist. Any spike in the radiation sensors forces you into the solar storm shelter, a tiny, shielded compartment lined with water and supplies, where you wait, still and thoughtless, listening to the particles from the sun slam into the hull. By day 60, the cognitive decline is measurable. You take a second longer to respond and reread instructions more often. Filters clog, and each small problem is a reminder that you are the only repair technician in 1,000,000 kilometers. Day 90 draws you into a region of space where radiation levels reach amounts no human has ever experienced before. You begin noticing vision changes, slight blurriness, and pressure behind your eyes, the early signs of fluid shifting around the optic nerve, slowly reshaping the eyeball. You check the EVA suit even though you won't use it yet. Everything must stay perfect. Between day 120 and day 150, Mars and Earth shift in their orbital positions. Communication delays stretch so long that conversation becomes functionally impossible. The loneliness becomes structureless. A major mid-course correction happens deep in this period, requiring hours of thruster monitoring. It drains you. Bone density loss is now measurable in medical telemetry, and even perfect exercise can't stop it. You know now that returning to Earth, even if you could, would be physically punishing. Day 150 through day 180 marks the approach phase. The spacecraft must prepare for the landing sequence, and everything on board needs to work flawlessly. Cosmic radiation exposure has now reached the life-tier limit allocated for astronauts. Your physical ability has dropped by 40%. Day 210 approaches, and you begin the final trajectory adjustments. Your thinking is slower, and your vision is subtly warped. Your heart works differently. Your bones are thinner. Your entire physiology has adapted for microgravity, and now you will have to struggle to survive the gravity of Mars. Atmospheric entry begins 15 minutes before touchdown. Mars has barely 1% of Earth's air pressure, and there's almost nothing out there to slow you down. You're strapped in, heart rate elevated. Your weakened body is preparing to feel the weight again. The spacecraft slams into the upper atmosphere at hypersonic speed, and for the first 3 minutes the thin Martian air bleeds its velocity. Heat builds across the hull, rising fast, then falling away just as quickly. Peak heating lasts less than a minute. The engine burn lasts another 5 to 7 minutes. Your arms feel heavier. Your weakened bones and atrophied muscles protest. Any deviation here would be catastrophic because the thin air gives you almost no margin for error. Touchdown comes as an impact you feel in your spine. You have survived landing. You wake up on Sol 1 to a planet that looks alien and empty from the portholes. Your legs tremble the first time you test them. This morning you have to verify hull integrity, run life support diagnostics, and check reactor telemetry. You send the first delayed message home. It takes 45 minutes for an answer. You do not step outside. Instead, you crawl through the vehicle and log your first medical data. The habitat inflates itself up beside the lander. By night, you sleep shallow and fast, your vestibular system trying to grasp for 0.38 g of Martian gravity. Sol 2 begins with the first EVA. The first step onto the regolith is cautious. Mars' gravity is kinder than Earth's, but your bones are porous, your muscles thin. The dust is everywhere. It clings, it magnets, it finds seams. You walk to the pre-deployed hardware, photograph nuclear reactors from a distance, and tape a visual inspection into your log. The on-site utilization unit sits quiet, awaiting power. By evening, you sleep inside the habitat, which feels like a blessing compared to months in space. The hazards of the red planet are not theatrical. Regolith contains perchlorates and razor-fine particles that abrade seals and clogs filters, and it's also highly toxic. Temperatures are extremely low. Daytime surface temperatures can hover around minus 20 degrees Celsius, while nights plunge to minus 100 degrees Celsius. Mars' atmospheric pressure is effectively near vacuum, and humans would not survive exposure. Moisture in lungs and eyes would boil instantly. There is no magnetic field, and the thin air offers no radiation shielding. You are still exposed to solar storms and cosmic rays. Your vision has new distortions as fluids within your skull settle differently. Week 1 is brutal. EVA walks, cable burial, reactor monitoring, and constant equipment maintenance. Dust storms roll in, the sky drops to twilight, and you retreat into the habitat. Outside, wind speeds are mild as Martian atmosphere is thin, but the dust is the one that does the damage. As days slide into weeks, your bone density keeps falling despite daily exercises. EVA walks leave you breathless. Your heart has weakened. A simple climb into the rover requires recovery time. Cognitive checks show a scary latency in decision-making. By week 3, the outpost functions like a system, but your body continues to change. Minor wounds heal slower, joints ache. You sweat inside a suit and freeze in a shelter. Radiation exposure on the surface adds to the cumulative lifetime dose you already have. For months, your transmissions follow the same pattern. Habitat logs, medical updates, science reports. Then one evening, Earth receives something different. A full bandwidth emergency uplink, tagged with priority flag. The packet is enormous. Raw data, environmental readings, suit telemetry, and at the top of the transmission is a single line typed manually. We were wrong about Mars. Mission Control attempts to open a live window, but the storm has already rolled over your site. A global dust event, the kind that swallows the entire sky completely. In your final transmission, The data you sent was painting a picture far more brutal than any simulation had predicted. The human body degraded faster and deeper than medical models projected. Radiation damage accumulated at rates no known method of shielding could change. Cognitive decline was devastating and irreversible. You never came back online.